Welcome you all. In this video, we are going to discuss about how to determine liquid limit and plastic limit of a fine-grained soil as per IS 2720 Part 5. As we all know, liquid limit and plastic limit are index properties. In fact, they are consistency limits. So they are widely used for classification of soil, and also, in fact, a parameter like liquid limit can be used for even estimation of compression index that we are going to discuss in the future chapter, consolidation of soil. You see, what do you mean by consistency limits? Here you see, consistency means once you see water is adding to soil, so how its consistency is changing. Here you see changing. Here you see solids to semi-solid, semi-solid to plastic, plastic to liquid state. So with addition of water, the water changes. With addition of water, water is trying to change the consistency of the soil. So here consistency means changing from one form to other form. Here you see the water content. Here you see liquid limit WL. This is liquid limit. The water content at which the soil changes from liquid to plastic state. And here you see plastic limit, the water content at which the soil changes from plastic to semi-solid state. Now we have shrinkage limit. This all together, liquid limit, plastic limit, shrinkage limit, all together we call Atterberg's consistency limits. So now these three consistency limits we are having. In this experiment, we are going to determine the first two, liquid limit and plastic limit of soil. Now let us proceed now. I will explain each and every step. Here you see, first initially whenever you are conducting liquid limit test, you can see here, one can see here, this is the Casagrandis liquid limit apparatus. So one can see this is a cup actually. Now you see we have spatula, a grooving tool. This is a grooving tool. We use it for cutting the groove. So I will show you. Now you see this is a soil specimen. So once you see, you keep on adding water. So you see the soil, how you prepare, that is also very important. This is a air-dried soil passed through 425 micron sieve. This is the soil, it is processed actually. It is the soil actually which is already air-dried and passed through, pulverized thoroughly and passed through 425 micron sieve. This is the, see, one can see the soil sample in the evaporating dish. Now you can add water sufficient quantity and then you just mix it, and now you see just fill the cup the way our friends are doing here. They are filling the cup. Now after filling the cup, one can see now. So now this is the way we use it to cut the groove by using groove cutting tool. Here you see grooving tool. Here you see after cutting. So this is the groove portion. Now what you will do? Now we'll apply the blouse. Now we'll apply. Now we just rotate this handle. So we use it to apply the blouse 2 revolution per second. Now one can see now after applying blouse, now this groove comes in contact for a distance of 13 mm. I can tell you half inch, 12.7 mm, or some books write 12 mm. So anyhow, the groove will comes closer for a distance of 13 mm. Till that we have to apply the blouse. So now initially I have taken a soil, a quantity of soil as mentioned in code is 120 grams, which is air-dried and passed through 425 micron sieve. Now what we will do, this is the trial number 1. In the second trial, in the same process is repeated with increasing water content. Now you add water more than what you added earlier, then repeat the same procedure, cut the groove, and then apply the blouse. So now you see, whenever you see, here I will explain what happening. Whenever you see increasing water content, if somebody is increasing water content, so number of blows are going to be decreased, because you see, because of flowability could happen fast when the water is more, water content of the soil is more, the flowability will be more. Now you see what is happening here. You see soil is trying to change its consistency from liquid to plastic state. So here we are ensuring flowability. So now here you see, in fact, this is the rubber base actually. One can see this is the rubber base, and the height of the ball of the cup is 1 centimeter. 1 centimeter. Here you see what happening here. Whenever you are adding water, keep on adding water, the number of blows are going to be decreased. But you see, to get this straight line, we need to select number of blows on log scale. That's why you should use semi-log sheet. I will show you. So select logarithmic scale for number of blows. For water content, a conventional arithmetic scale is enough. Now this is the flow line, and this is the slope of the flow line is flow index. So one can easily tell this is W1, then it will be, here you see N1. So like that you see, here it is W2, then it will be N2. So that's why here you see the slope is Y2 minus Y1 by X2 minus X1. W1 minus W2 by log 10, N2 by N1. Sometimes we use it to say minus here. If anyone found minus, so one can say that if anyone found minus, so W2 minus W1, so you may have to put minus at the beginning. Otherwise, if you are writing W1 minus W2, because what it is saying actually minus, once water content increases, number of blows becomes decreases. So that's the, so it is a downward trend. Try to understand, this flow curve shows a downward trend. So now you see, I will show you observations made by our students in the trial one. They have calculated the water content. Many times I used to tell you water content is mass of water present in soil by mass of dry soil. Here you see, I have taken can number 8 in the trial one, and the number of blows 40 minutes, 40 blows taken for this groove come in contact for a distance of 13 mm. So when they apply 40 blows, so we have a Milky Way, it will count the number of blows. So no issue. Now you see, once you see applying the blows, so 40 blows, then groove comes in a contact for 13 mm. Similarly, repeat the procedure. Here you see in the trial 2, we have taken another can number 2. Now this is the number of blows taken are 30. So this is the water corresponding water content. So in the trial 3, we are adding water once again. That means you see, in this trial, we have selected we want to determine the water content once again in the trial 3 with addition of few more water. Now you can see this is the can number and number of blows. Now this time is 17. So we have done 3 trials. Now you see this is the plot actually. As I mentioned, this is the water content on y-axis in arithmetic scale. Here you see 10, 20, 30. So water content is expressed in percentage. So here 10%, 20%. So that means 1 centimeter is equal to 10%. Now coming to logarithmic scale, I already mentioned number of blows should be plotted on logarithmic scale. Here you see I have 0. Here you see I have 0, 10 power 0, 1, like that you see 10 power 1. This is 10 power 1. We have 10 square. So this is enough for me because my number of blows are between 0 to 150. Now you see, here you see I have 10 power 0, which is equal to 1. Now 10 power 1. Now 20, 30, 40, 50, 60. It's enough for me. So it goes 90. Now it reaches 100. Now here you see I have number of blows. Here you see I have number of blows in the 17, and also here you see number of blows 30, number of blows 17. In the first trial we know that we have number of blows 40. The same are plotted here for 40. Here you see water content is 36.7. One can see clearly This is 36.7. Now for number of blows 30, water content is 51.75. Here you see this is for 30, 51.75. Now one can see now the number of blows is 17. Now one can see 17. So for 17, the water content is 64.34. Now, so we have 3 points here. Better to take 4 observations. So here we got 3 observations. Now you see, I'm trying to pick up the liquid limit. According to Casagrande, the water content corresponding to 25 blows is called liquid limit of the soil. Here you see for N25, number of blows 25, the water content corresponding to number of 25 blows is the liquid limit, which is equal to 55. So in the same enthusiasm, we have conducted plastic limit also. But it is good to discuss about the importance of liquid limit. We got liquid limit 55 from this flow line. Here you see from the flow curve, we got the liquid limit 55, the water content corresponding to 25 blows. Now if it is greater than 50, it is highly compressible. If liquid limit of the soil is greater than 50, which we are trying to call highly compressible. If it is less than 35, it is low compressible. 35 to 50, it is intermediate compressible. So high compressible designated with H, intermediate compressible is I, low compressible obviously L. Now we can see how to determine. I will explain plastic limit. Here you see, take 30 gram of soil, and as I told you, it is air dried and passed through 425 micron sieve. Add some water, and you see what we are doing here. You see, we are making a rolling. This is a rolling thread method. We are trying to roll the soil. So then the diameter of the thread is 3 mm. Here you see, and also it has to show the crumbles. So once the crumble started, that indicates that your soil consistency changes from plastic to semi-solid. Now the water content at which the soil changes from plastic to semi-solid is called plastic limit of the soil. So we have to make a 3 mm thread. You should roll the thread, and its diameter should be 3 mm, and it should start crumbling. So the way our friends has done plastic limit, in fact, they have done 1 determination, but it's better to do 3 determinations with average, which gives more accurate result. Here you see can number, can plus wet soil. Many times I'm telling how to determine water content. Plastic limit is also water content. Liquid limit also water content. That is the importance of determining water content. Now it's time to discuss how to determine plasticity index. Plasticity index is equal to liquid limit of soil minus plastic limit of soil. I got liquid limit 55, plasticity index 17.75. Just now I shown you. Here you see we got 17.75. So by making rolling thread 3 mm diameter, and it should crumble. Now you see I got IPA line. I can tell you IPA line. A means Arthur Casagrande is the person who invented this all. So A means Arthur Casagrande. IPA line is equal to 0.73 LL minus 20. I will explain in my next lecture about IPA line during discussion in soil classification, especially classification of fine grained soil using plasticity chart. Here you see I got 0.73 into 55 minus 20. So I got 25.55. So because liquid limit is 55. So my IPA line is 25.55. IP is 37.25. So IP is greater than IPA line. If your plasticity is more than IPA line, then you can say that the given soil is clay. The given soil is clay. For example, if someone say that if IPA is more than IP, then it is called silt, yam. So therefore, finally, we can conclude that the selected soil is a fine-grained soil, and the thing is, it is a clay, and it is a highly compressible clay. Therefore, the given soil is highly compressible clay. Why I am telling highly compressible? Because liquid limit is greater than 50. Why I am telling clay? Because IP is greater than IPA line. You just see here, plasticity index is more than IPA line given by the Arthur Casagrande. If plasticity index is more than IPA line, that is 0.73 into LL minus 20, then we can call it as clay. Therefore, finally, the given soil is highly compressible clay. And you can determine even the slope of the flow line. So W1 minus W2 by log 10 N2 by N1. I got here, you see, I have taken two observations. One is 64, another one is 34. Now you see corresponding number of blows is here, you see 18, here it is 40. Now you see 64 minus 34 by log 10, 40 by 18, I am getting 86.50. And it is possible to determine toughness index also by conducting liquid limit and plastic limit. Finally, I'm trying to say we can determine index properties like plasticity index, which is equal to liquid limit minus plastic limit, and flow index, and also toughness index. Toughness index is a ratio